Hi and welcome again. Today we are talking about binary search trees. Well, a binary search tree is a data structure that is based on a binary tree. But we have some conditions on the nodes, and we say that our left subtree is always smaller than the actual node, and the right subtree is always greater or equal than the actual node. And what that means we will see later in a nice example. And one really good thing with a binary search tree is that it has an average time of log n for searching data in the tree. But it also has a time of n in worst case, and that is if we input our nodes in an ordered, in an ascending or descending manner. What basically means that we end up with a normal list. Alright, so let's have a look at the insert operation in a binary search tree. We insert here from left to right of our array, and then we start with the 5. Alright, since there's no node in the tree, we say our root node is the 5. As next we have to check, is the 8 greater than the 5, or greater or equal, then it goes to the right, or if it's smaller, then it goes to the left. Since it is greater, we go to the right. As next we have to go to the 6, so we start again at the root and say, is the 6 bigger than the 5? Yes, it is. So we go to the next node. We are now at the 8. And there we make the comparison again, and we say, is a 6 smaller or greater than the 8? And it is smaller, so we have to attach it as a left child of the 8. And we keep doing so. The 9 goes then to the right of the 8. The 12 goes to the right of the 9. Alright, the 4 is now, we are again at our root node. So the 4 is smaller than the 5, so it goes to the left node of the 5. Then the 1 goes to the left node of the 4, and the 3 is also smaller than the 4, but bigger than the 1, so we go into the right node of the 1. Alright, and that is how we basically construct a binary search tree. And as you can see, all nodes on the left are always smaller than our actual node. Here, for example, the 4, 1 and 3 are smaller than on the 5, and the 6, 8, 9 and 12 are greater than the 5. And if we have a look at the node 8, there we see that the 6 is smaller, so it is on the left side, and the 9 and the 12 are bigger, so they go to the right side. Alright, so let's search now for a value. Let's search for 3. So we are at the 5. We say, is it equal to our 3? No, it is not. So we have to go to the left because it is smaller. We are now at our 4. Is the 3 greater than the 4? No, it's not. It's smaller. So we go to the left side again. And there we are at the 1. Is the 1 smaller than the 3? Yes, it is, so we go to the right side now. Alright, that is how we traverse it. Let's make another example. Let's search for the 7 here. The 7 doesn't even exist in the tree. So, at first we are at the 5, and we see the 7 is greater than the 5, so we have to go to the right side. And we are now at the 8. So we have to have a look now at the next node. Is the 7 greater than the 8? No, it's not. So we go to the left side. And now we are at the 6. Now we have to look for the children of the 6. Is the 7 Smaller than the 6? No, it's not, so we have to go to the right side, and there is no actual right side. The 6 is a leaf node, and that means we didn't find the 7. So we are actually done and can say we didn't find the 7. So we had to make 3 comparisons for a tree of the size of 8. And that is a really good runtime. Alright, so let's implement that now. At first we create a new file called binary search tree.python, and then we create a class called binary search tree. And now we need a helper class that represents our node and its child nodes. So we say class, and we make it private, and there we say left for our left child. We set them none for now. We say right for our right child, set them none for now, and the same with a value. And then we create a constructor method that gets the value and sets it in the end. So self.value equals value. So we save a lot of time with that. The next part we need for our binary search tree is a root node, so we say root equals none here from the beginning, and we make it private. So let's create the insert method. So let's say def insert, and that gets self and a value. And here we can write inserts a value into the binary search tree. Alright, so what we have to do first is we have to check if our root node is none, because then we are done with it. We just have to set the value for our root node. So if self.root equals none, then we say self.root is a node, and we give it the value. And we have to use self here because the node class is an instance of, or is an object of our binary search tree, a property to say it right. Alright, and with that we can return here. What do we otherwise? Now we have to go through our tree, and once we find the right node, then we have to insert it there. So let's create here a while loop, and for now I just say true, and I say here exit condition. Alright, so what we have to do is we have to tangle through our tree. So I want to get our current node here. That is the node we are always working on, and I set that in the beginning to self.root because we want to start the comparisons with our root. So if we are here, we can say if current node dot value equals none. So there is no value set yet. Then we can say current node dot value equals to our value that we want to insert, and then we can simply return here because we inserted it and there's nothing else to be done. Alright, what do we want to do otherwise? Now we have to check if current node dot value is or other. Let's start with the value we want to insert. If the value we want to insert is smaller than the value of the current node, then we have to insert a new node, and therefore I say current node dot left equals to here we need self again, node. And I give that for now a none value, because up here we check if the value is none. We just have to create the instance of our left property here in our node class, because for now it is simply none, and we needed to have the physical address of an actual node. So we go in here, let's say here node is leaf if the value is none, and here we say traverse to the left because the value is smaller, and here we can then say current node equals to current node dot left. So we hang our us around the left of the current node. Otherwise, if it is bigger, then we have to traverse to the right. And there we say else. And there we have to do the same again, just with right node, current node dot right equals to, we create a new instance of it and give it none as a value. And then we have to set our current node equals current node dot right. Alright, so now let's have a look at the exit condition here. We basically return whenever we find the value none. Since we don't set the value on the creation of the node, we will always achieve that. So we can leave it here with this condition. What we could also do is we could check here if current node dot value equals none, and then we do this here outside of the actual loop. So we go down here, insert that. Oops. Now we are outside there. Let's bring that in form. And here I want to remove one of those. So we go in here and say here just if that, then we keep traversing through it. That is our traversal until we found the appropriate node, and that is exactly there. So that is maybe a little bit cleaner to implement. And now we don't even have to do the return here. Here we simply traverse and create the nodes, and then we go in here. Alright, what I missed here is we have to check if the current node dot left is not already set, because when it is set we don't want to create a new node. So we say if current node dot left is equal to none, just then we want to create the new node. And we have to do the same down here. So we say if current node dot right equals to none, then we want to create the new node. Alright, so far so good. Let's create a quick print method where we say def print, and we print it in breadth first traversal. So we say BST, and that just gets our self. Alright, and here we can write print the tree in breadth first traversal order, and here we give it a BST as an abbreviation, so everyone knows what is meant with it. And there we say if our root node is equal to none, we can go in and say print none, and then we are done, we can return. Otherwise, we have to print the current node and we have to print all its children. So we need actually a queue here, and we can initialize it with our self.root. And then we go here and say, while our queue is not empty, so we do that by checking the length of our queue, while the length of our queue is greater than 0. We go in and say, okay, we want to work on our first element of the queue now. So we say queue or node, let's call it node, equals to queue, and there we take the first element. And since we are done with printing, then when we are done after printing with this node, we can already remove it from our queue. So let's say queue equals queue 1 to the end. So we basically take the same queue, just with the first element removed. Alright, so now we can check if our right element, we start with the right element because we want to print it in that order. We say if node.write equals or is not equal, let's do the value here, is not equal to none. Then we want to go in and add node.write to our queue. So we say queue.append node.write. And also we say if node.left.value is unequal to none, we append it to our queue and say node.left here. And in the end we just have to print our node.value. And then we are already done with running through it. So let's try it out. Alright, if name equals to main, so we jump to our main function. We go in and at first we create an instance of our tree. So we say BST, the abbreviation for binary search tree, equals to, here we say binary search tree, and then we have some data points. Let's take the same data points as we had earlier. So we say here we have 5, we have 8, we have 6, we have 9, and then we have 12, 4, 1 and 3. Alright, and now we go through all of our data points. For value in data, we say bst.insert our value, so value. And then in the end we go in and say bst.print in Bradford traversal. Alright, so let's try it out and hope that everything works fine. And if we go in, we become here, or we get here a none type, has no attribute value in 57. So here the right value is none. So what does that mean? That node.write is equal to none. So we have to check here if that is not none, and here if that is not none. So let's print it now. We just get the 5 here. Alright, so let's make some error checking here, and I wanna have a look here, and I want to simply print the current node dot value to check if our items were inserted in the right manner. So we don't even get in here. So what does that mean? It means that self.root is equal to none always, and we don't even go in here. So we don't set the value. Let's check if here is everything fine. I think so, but yeah, who knows? Maybe there's a mistake already. That works fine. Here we get all the values, so we can remove this here. And now let's have a look here. So let's go in here and just say print value and see what happens there. So we definitely go in there once. So let's go in here and say print current node dot value, which should be our root node. And this is completely fine. Alright, so now the next step is to go in here. And here is a mistake in our while loop. We check and say if it is none, then we want to abort the loop. So that should work now. Do we printed everything? Yes, we do. I don't wanna... No, that is fine here with the print. That is our actual print method. So let's try it again. And now it works fine. It was just the exit condition of our while loop. And if we have a look here now, that looks perfectly fine. I just see that here it seems like these are a little bit, they are in the wrong order where we printed. So we can go in here. And I think we have to swap these two. So we work at first on our left and then our right. And that is completely fine now. So we print it in the right order and that looks really good. And if we check it, we print all the layers as they are supposed to be. Alright, so now that we have created the tree, we can also create a search method. But I want to leave that for you because it is very similar to the insert method, just that we have to break at the right point here and insert if value equals to our current node value, then we simply return, and that's basically it. Alright, ladies and gentlemen, if you liked this video, if it helped you, then give it a thumbs up. And subscribe to the channel. You will find the link to the source code in the Git repository as always. And so post me down in the comments below what was your solution or to the search method in the end. Or what do you think about the video? What would you like to see? Alright, that's it for me today. Have a great day. Bye.